Yes, thank you very much. So I'm very delighted to be able to support to this course, but also to the activities of Aalto University, because you have all the interesting essence which I'm interested in: the science, the business, and art. And I will a little bit cover my interest in my presentation. And at the end, what I will present now is various things from all my diverse experiences. So it might seem random things, but at the end, this is just to motivate that do whatever you would like to do, what you feel interested in, and then you will find your own career path and so on. So the nanotechnology and all these technologies which we hear about, they are nice, but the people make the change and people make the business and so on. So that is the most important part, which is the essence of my message today. So I'll pick up my So now you should be able to see some slides. Yes, so I had some title here, and I have background in materials and nanotechnology materials. And like Mikko, I had a strange career because I started with research 1995 and got my PhD in 1999. So I was deep into the physics and in particular the crystal growth. So that was my genuine interest. And then in 2005, I started to become interested in the entrepreneurial things, how to make usefulness from our research and so on. And then I've continued on that one. And now I'm really interested in this innovation perspectives on how to make more usefulness from the research. Because it's a big challenge to go from the research to a paying market so we can have business. And like Mikko presented, you can have successful technologies, but then the market collapses and you don't have the same opportunities like planned from the beginning. So here there are many things which happen and everything is unique. What I describe is sort of that there is entrepreneurial research which can be also an academic career. So if we make more usefulness, this will be appreciated also in the academic world, not only publishing papers and all those things which are more traditional. And now when we motivate research, then we have to target Agenda 2030 goals, which is nice, but they are very broad. So we should find some ways how to propose that we will do this in a more practical way. We'll find the next avenue from where we are, and then over time we will reach the Agenda 2030 goals. And from the research, I think the entrepreneurial interest, for those who are interested in that, can be a way to motivate such things. And I have also been student, and in Sweden, when we start, we have this overall. So we take it on, and then we are initiated in the beginning. So in 1989, I started my undergraduate studies in applied physics and electrical engineering in Linköping. So that was the start of my professional career. And during these studies, then I became more and more interested in the materials and the growth of materials. And when I picked up the PhD studies, then I started with silicon carbide. So here you see a schematic of the silicon carbide principle. So we have a source of material at the bottom, and when we heat up the silicon carbide, it sublimes. It forms vapor species from the solid material, and those vapor species are transported to a growing surface. So this is the basic principle which has mostly been used for silicon carbide, and which I studied also. And the purpose over time is to make wafers. In the 90s, there were a lot of research and nothing was really mature, so everything was new, research was new, it was the fun times. And on over time, this has matured, and now there are 6-inch wafers of silicon carbide available, and it is a market, paying market. So it has gone over these 20 years from initial research to something commercial. And one of my fields of growth of silicon carbide was to take this method and then we modify it. Instead of having a silicon carbide powder as source, we had a ceramic silicon carbide. We shortened the distance, and then we cannot grow this type of bulk material to produce wafers, but we could keep the high growth rate of the process, so we could grow thick layers of silicon carbide. And the main motivation at this time was power devices. So if you want to convert 10,000 volt and control that one in a power device, you need thick layers to handle this. So it was possible to achieve. Here you see a wafer, and this inner circle is a thick layer, and in this case it is about 100 micrometer. So this was a nice achievement. So we got these thick layers and so on. So that was highlight of my thesis, sort of. But these layers were not useful for the power devices. They were thick layers, very nice structural quality, and so on, but the purity was not enough. So the highlight of my thesis was a process which was not useful. And that was 4 years of studies. And then I was in idle mode for a while and did some research and continued these things. And then in 2009, I met Satoshi Kamiyama, who comes from Meiji University in Japan. And he had an idea of silicon carbide as light-emitting material. So if you dope it, you can have light coming out from the silicon carbide. So then suddenly, our process for these thick layers became relevant again, because he needed thick layers. He didn't care about the high purity because he wanted to introduce dopants to create light emission. So then we became really unique with our method, and we started a collaboration in this field. And this was actually my first own research area where I found some fundings and so on and started to have a career. And this is also where I came interested into the energy and environmental applications. Instead of power device, we have other approaches like LEDs and solar cells, and that became my field of interest in the research. And also there, it was so much interest in this that we created a joint venture, and we made a technology transfer of our process to a Japanese joint venture. And this was when my entrepreneurial interest really kicked in, because I was super happy that someone was interested in our research findings and our process, not only to publish paper, but someone actually acquired this technology. So we made a technology transfer, and now there's an ongoing things in Japan on this. It's still early stage because there's so many things in the physics to be sorted out still. But the nice thing is that this fluorescent silicon carbide, the light-emitting silicon carbide for this LED, it kicked off a research area, and we had collaborations, and the collaboration with Meiji University is really nice, because that is the group where they got the Nobel Prize for the blue LED. So in this picture, you see me on the right side, then Satoshi Kamiyama, and then Isamu Akasaki, who's the one who initiated the research in the nitride material for the blue LED, which was then used together with phosphor to create the white LED. So there was a lot of collaborations and nice and new things. So that was really fantastic. And this group is very prestigious, and that they got the Nobel Prize. And I'm a simple guy with Finnish blood living in Sweden on the countryside. So it was very happy event that we got this matching. And it was not planned matching from the beginning. It just happened due to the nature of interest. And then we had these things and something matched together. And we have also achievements that we have light coming out from the material, which is nice. And what I would like to point out here is that on the left side here, you see high NO. So when I had this possibility of applying for project for the fluorescent silicon carbide for this exciting research, then there was a Nordic call. So then I knew one partner in Germany, because Germany was part of the Nordic call, but we needed to be free. So then I was thinking, okay, I need someone on the optical properties because we are growers and Germany is grower, and we can do doping with his material and so on. But we needed someone on optical properties. So what I did was that I was Googling Denmark Technical University optical properties research and so on. So then I found one guy who had got an award or something for studying optical properties in materials or LEDs or whatever it was. But he was not interested. So when I emailed him, he said that, no, I'm not interested. But I have a colleague here next to me in my room. I'll give this email to her. And that was Haya No. So that's how we started a collaboration in 2010. And over time, this network and collaboration has continued. And the good thing about that is that when you have good ideas with good people, there will be fantastic things happening in some way. And just to mention what we are doing now, Haiyan got the idea that to apply for a frequency comb in silicon carbide. And this is a European FET open project. And the idea is that we have silicon carbide, we can have a signal and split the light to several wavelengths. If you have an original wavelength, you can split it to several. So instead of having 64 lasers like in a server, you can have one which splits the signal, and then you can create communication. And if you compare how much energy you save, instead of having 64 lasers, you have one, there's a tremendous amount of energy. And also the communication can increase a lot. So this became this type of European project, which is radical technology development and so on. So from the network, the initial findings and so on, what we had, it came to this stage. But it was not planned from the beginning, and it would never have happened, most probably, unless we started this collaboration, exchange and so on. So that was another thing which popped up from the research. And let me go now to the nanotechnology part, because now I have been talking about silicon carbide and fluorescent silicon carbide. And silicon carbide consists of silicon and carbon. And we have the graphene. I think you have had a previous talk on graphene and some applications. And basically, if you missed that lecture, then graphene is a carbon atom, which you have in one layer only, one atomic layer. And if you have studied the Nobel Prize in medicine, chemistry, and so on, very often the carbon atom is there. Either the researchers want to put them together in some unique way, or break the bonds to put it together again, and then you have some type of medical application, for some pills or something which is good for the body. But it's a carbon atom which is the essence of those things. So the carbon atom itself has really nice properties. And when you add on that you have only one atomic layer, then you have quantum effects by that. So if you combine the carbon properties and the quantum properties, then you have the graphene. And this is basically why graphene is so super, super, super exciting, because it's not only one or two interesting properties, it's a plethora of properties which makes it interesting. So there, it has very broad application, for example, in processors, because the electron moves 100 times faster than in silicon, for example. So you could make processors which are several times faster than today. But also, this can be used like in composites. So you reinforce existing material to make composites which are stronger and maybe not as heavy as before, so they become lighter. But maybe also we can build in that there are electrical conductivity in this composite, and then you can use this for many purposes, and so on and on and on. And you have most likely heard about this, so it becomes like big boom of the material interest. And this is also why there is a graphene flagship by European Commission. It was proposed 2012, and this type of EU big project, then it was the graphene was supported with 1 billion euro to go from the research to market. So it wanted to facilitate that this happens. And graphene was selected because it has all these nice properties. So it's a really big belief, and that is what is happening. So graphene flagship you probably have heard about. And very nicely, Sweden is coordinator of this graphene flagship. So we have Jari Kinaret, who's leading this one, and he made tremendous amounts of work to get this graphene project, because before it was accepted, then he and colleagues were going to Brussels talking with politicians, and Jari is working in theory of physics. So you can imagine we who are in the physics talk with politicians. It's a big gap, so you need to communicate many times before you can persuade someone to give 1 billion euro. So that was a great achievement, and of course there was a Finnish blood here. And like in Sweden, in flagships, maybe the experience which Swedish people have is related to the flagship of Vasa and so on. So it's very nice to have a Finnish person steering these things. And here there is a roadmap from 2013 to 2023. So now we are close. Now 8 years has passed in this graphene flagship. So that's something which is happening. And these things are very good examples that if you would like to get something from the research to be used, you need to push this. We can take an example of the LEDs which you can buy today. They are in store, so they have replaced the light bulb and so on. But in 2008, European Commission said that we will phase out the light bulb. We have a program here. The light bulb will be phased out, and you have to follow these things. And it was a big market in the light bulbs at that time. But since the European Commission said that we will phase this out, all technologies had to develop. So this pushing from above, sort of, if European Commission says that we will do this, then industries will follow. If this would not be pushed, they will continue to try to make business as long as possible. There's money. So the transition would take much longer time. So this is why research and so on has to consider the programs which are nationally in EU, but also regionally, to align with them, and then more things will happen. So I will mention a little bit of this afterwards also. And if you imagine 10 years from now, if I had a mobile phone, 10 years ago I could call with it. That was the main thing for that one. And if you compare what you can do with your mobile phones today and so on, it's a big difference. So you can imagine 10 years from now, what will happen, how will they look like, and how many things can you have in those. So there will be tremendous things happening. Let me come a little bit to the graphene on silicon carbide, which is my special area, or one of them, where our group has been working. And then we come back to the silicon carbide wafer. So we have that one, and earlier we were growing silicon carbide films on these wafers. And then we're using a high temperature process. And in case of silicon carbide, when you go to high temperature, you have the vapor species which are formed. You have silicon, 2 silicon, 1 carbon, 2 carbon, 1 silicon, and so on. So they appear in the vapor phase. And when you have poor conditions of these things, because everything is in a graphite environment, then you have a shift, a difference of the silicon and carbon. So this is when this happens, when you heat up and you have poor conditions, you actually graphitize the surface, which is very bad from the crystal growth point of view. So when we did this in the epitaxy, it was very bad, very depressing. But then that's also, it became a natural process for thin graphitic layers on silicon carbide. So actually, in very early, one researcher from Chalmers asked our group, can you make these thin graphitic layers purposely? Because we did some annealing of ion implanted materials and so on, and then there was thin graphitic layers, and he wanted to study that. And we thought it was embarrassing to have such a process to graphitize the silicon carbide. But when he studied that one in their group, then it was shown that it was a very high quality of the graphitic material on the silicon carbide. And curious as we were, we made it thinner. And 2005, we had one layer of carbon on silicon carbide. So that was graphene on silicon carbide. We did not know so much what to do with this and so on. So we asked the guy to simulate and so on the heating. And we did not have funding. And then we had a master thesis trying to control these ones. It was not successful here, but we continued. And then we could control it. And then we had a very nice publication by colleagues demonstrating the quantum Hall effect using our epitaxial graphene. So we were very early with graphene on silicon carbide. And here there were also many collaborations in research, and they were asking for materials so we could publish, and it became more and more requests. And then we were thinking that, oh no, we cannot have this. We have projects to focus on, and we cannot give free material for papers in other topics and so on. So then we were thinking, how can we reduce the number of requests of our material? Then we were thinking, we asked them to pay. So we started the company, and researchers usually don't want to pay for material, so they prefer to have it for free. But actually it turned out that some of them would like to pay for materials. So our company had sales from day one, not so big sales, but at least it was a good beginning. And that was the next kick in my entrepreneurial interest, how to make the business from the science. But it's difficult to make business when you're early in the materials development because the applications are not there, which means that the market and high volume numbers in sales are not available there. But the entrepreneurial process is something which is very interesting to follow because it triggers and gives experiences for other things. And in the silicon carbide, just to mention some of you who are interested in the deeper physics, when you heat up the silicon carbide, you have these vapor species, which I have been mentioning. So they have different vapor species pressure. And depending on the temperature, there's a change happening in these ones. So temperature is very important to control these ones, both for the growth, but also for the sublimation to make the silicon graphene on silicon carbide. And when you look at the ratio of these, the temperature changes the ratio of silicon to carbon over this. So this is also an influence, an important part, how to control to have monolayer over large area. Because the benefit here is that we have silicon carbide as wafers, large area, not these flakes, which you have from other processes and so on. We have the wafers, and silicon carbide is a robust material, and then the graphene on silicon carbide is robust because it's bonded. It grows from the silicon carbide and it's bonded to it. So it's a robust, good system which can be a platform for the electronics and sensors and things when it interacts with molecules. We believe sensors is one area. And also in the physics, if you happen to be involved in growth, you know that you have steps which are formed, and one way to grow material is to grow step by step by step and grow the material. And there you can have step bunching, so one step accumulates to another one, and then you have step bunching and becomes thicker, and that's basically a problem, but also an opportunity. And when you go into the very fine details, you can see in the bilayers, silicon and carbon, there are several ones depending on which type of silicon carbide you have. Then it becomes quite a complex process. So there's super many things to study here in this field. And then the surfaces can have different appearances. Sometimes it's not useful, but sometimes we can use these surfaces for intentional properties. For example, in these steps, if we would like to make them bigger, then actually graphene forms at the edge of the step. So instead of having a layer, we have a ribbon of graphene on these surfaces. So that's one way how to use the step bunching intentionally for creating. And then over time, we can do this on the different polytypes of silicon carbide, because when you have silicon and carbon, you can stack it in different ways, and then you have different polytypes of silicon carbide. And when you do graphene on that one, there will be different things happening. So I will not go into the details because I want to introduce some other things, but there are super many exciting things to be done here. And also, one thing to get into new avenues in the nanotechnology and materials is that, for example, if you have other carbon allotropes, here is a graphene flake, then other people are studying how to make flakes. This is one of my colleagues who also started the company. He's using graphene oxide and is able to produce that one. And there are other types of graphene flakes. In his case, they're working on the heavy metals removals using a filter with this graphene. But if we would like to combine these things, then we can add on functions on the material. So that's the novel research avenues which are still to be done. And over time, if you look into the graphene flagship and having some company formed, there is a long time before this is accepted at market. Maybe you have seen this type of curve. In the beginning, it's so super exciting. You have breakthroughs every day, like in graphene, it was mentioned. And then you explore that one, and then it becomes a little bit saturated. And then when you start to control this, to reproduce the findings, then there's not as much news value. So then it's not reported, and then interest falls down. And this is the valley of death, where interest is lost. Maybe investors lose the interest or whatever, or industries. But that's where you start to reproduce the things so you can control it and come to a market. And for materials, this always takes several years. In the case of blue LED material to the white LED, the initial research was done in 70s, 80s. You had the blue LED commercialized 93, and then 15 years later, you had the white LED on the big market. But that was 30 years. In our case, what we think is like in the future, so if we want to push in new ideas, we would like to combine these flakes or other carbon allotropes on the graphene to make something new. So we can use the properties from the different ones to make new things and so on. So this is just to mention, if you would like to make a master thesis work, I would recommend this topic, for example. And what we're also doing is that we have been modifying the graphene by ion irradiation. We can create modification of the planar graphene surface, and we can have high or low energy ions of different types to modify the surfaces. So that's a joint study with Priya Kaushik here, and so on. So those are things which are still to come from the graphene or silicon carbide activities. And let me mention a little bit more about the combinations and one exciting things. The cubic silicon carbide is the polytype of silicon carbide which is very difficult to grow. So it doesn't want to form. We have the different polytypes, 4H and 6H. They were studied from the beginning, and they are now commercial. You can buy wafers, but the cubic is very difficult to form. It's metastable, so that's why it's still behind its big brothers or big sisters in the silicon carbide research and also, of course, market. But when we had our method, which we modified by different things and also temperature, then we can have cubic silicon carbide to form from the process. So the initial process to make these thick layers for the power devices, if we dope the layers, then we can have LED activities. And when we have the cubic silicon carbide to form on the 6H or 4H, then we can have thick layers of cubic silicon carbide formed using this process or a modification of the process. So this also became a study in our research. And when I met one researcher at one conference, he was talking about, Antonio Marti, he was talking about this theory. We have a wide band gap because silicon carbide is recognized to have larger band gap than silicon. Hexagonal has 3.0 and 3.3, and cubic has 2.3 electron volts. And when he was talking about the solar concept, that you have large band gap material, which is around 2.3 electron volts, or 2.0 electron volts is the theory. And then when you add an intermediate band by a very, very high doping or other ways, then you can have 3 energy levels where the solar energy can be collected. So instead of 3 materials, you can have 1 material with this level. And then it turned out that the cubic silicon carbide doped with boron, which we were using for the LED project, fits nice into this model. So then we came into another research avenue on the energy side in our research. And all these things are nice research things and potential technologies and so on. But if we would like to fit these things into broader context, then we have to motivate it. And today when we are applying for research, then we need to motivate most often, how does this fit into the Agenda 2030 goals? Yeah, it's nice. There are 17 of them, but they are so broad. So one thing which will happen is that now European Commission, again, says that they tell regions, we have regions in our countries, and they are part of Europe, and we pay tax to European Commission, and they give it back to regions, so regions will do more economic growth. So some years ago, European Commission told the regions, find your areas of strength, where you have a little bit are stronger, and then we will give you money to grow in those areas, also the other areas, but here they will. So this is called smart specialization. And here the regions have found areas, so they are not as broad as Agenda 2030. Like in our region, advanced materials is one of the areas of strength. So if we can show that our research and our collaboration, it fits into the scope, then we have a direct, more practical motivation of our research. And I know a little bit of these things because I was involved in our region to support how to establish the advanced materials domain. And now there's an arena which is more active on these things. And also this is how I came into this innovation, make more usefulness. And my affiliation today, main one, is Alminica, which is an innovator, facilitator, helping with these things in projects. And I'm involved in the Frequency Com project on the innovation exchange and enhancement. So that's why I came into this avenue. But at the end, we will have experts and regions. They have matchings. They create the value chain in some way. And when we have more exchange in these things, we can demonstrate more that it fits into a technology value chain, a regional value chain, and so on. And these fits into the European context. So the technologies are nice, but they will not themselves go to a market. So this is something which is happening. And then over time, there will be collaborations between regions, between countries in Europe, but over time it will be international collaborations all over the world in some way when there's a natural partnership. And if we go back to the nitride material for the blue LED, where they had the Nobel Prize, that one is now used for creating the LEDs. So basically you can only buy the LEDs, the light bulb is phased out, it's gone. And that technology is very energy efficient, but also it is used in other contexts, which was not planned from the beginning. But for example, in the arts, if you have paintings, depending on the angle of the LED, which is very focused light, it's not that like the light bulb which is spread, depending on the wavelength you choose to have dominating and the angle and so on, then the paintings will you can experience them in different ways. And this is thanks to the LED technology, where you can use these things for such things. So it's very much involved in the art. And also on the society side, LEDs don't require the same type of input power. You don't need the 220 volt and so on. So then you can use this and spread all over the place. Like here are some buildings in Brussels when I was visiting there. So they had the LEDs which change every few seconds something. So it became much broader than its original intention. And the origin was the nitride interest in the research, then it was blue LED, and then white LED and these other things. So over time, the business opportunities or innovation opportunities will grow in some natural way. This is a very outstanding example, but whatever we do, similar things will be happening when there's a good basic thing. And what they are doing in Japan, they are facilitating the students, those who are interested. So I was listening to a talk at European Materials Research Society meeting 2 years ago. So Professor Amano, who also was one of the Nobel Prize winners for the blue LED, he gave a talk about this technology. So the funding agencies in Japan, they said that, oh, very nice with the white LED and so on, and we would like to have more. And we don't want that it takes 30 years. We would like to have it in less than 10 years. And Professor Amano said, oh, no, this is not possible. And then they discussed. And now what they're doing in Japan is that they have programs which facilitates that students who would like to become entrepreneurs, they are encouraged to do that. And for those who are interested in the reproducibility of research findings to production, then those students are encouraged to do that. And those who would like to invent new technologies, they are encouraged. So there are programs for these things and other support mechanisms like mentors and internships and so on. So this is something which happens, and it will come to our countries also in various ways. Maybe you already have it in some way or so. But this is something which is happening. And over time, we will need to go to meetings, and it will be more and more international. And we can create opportunities, like Imran, he's a visiting professor in China, and so on. So that will give another opportunity, and we will find partnerships and so on. And at the end, what I would like to point out is that these technologies are nice, prospective, but we never know what will happen if the physics work out, if the costs will be sufficiently low for it to be competitive, if there are political decisions, or if the people will no longer be available who are driving these things, inventors and so on. But at the end, the opportunities comes from exchange. So when we have meetings and also informal exchange like this, presentation, and when we have the question and answer in a few minutes, then we can create either inspiration, ideas, or even collaborations and so on. So networking is very much useful for careers and getting opportunities. So if we look into the nanotechnology or advanced materials, it can be very broad. But what we do today, the ideas which we have, and like Imran's research, for example, this is super exciting. It will be used in the future, and since this is in energy and sustainability and so on, it will be useful in some way. Maybe the way we intend and plan today, or in some other modified way when things change due to whatever is happening. So the future things is developed from materials today. And if we consider the climate crisis and all those challenges, then it's very good that we are doing this more and more. So I'm very nice to hear about the previous talk and this course and the combination of the Aalto University of the science, business and art. So with that one, I hope you have got some inspiration or ideas. I did not go into the detail of anything from the materials and so on. And I would like just to end now with also showing that in the materials, there's something which is called art and science from the crystal growth. And when I have been growing crystals, and we look in the microscope, we take pictures for the publishing and so on. But if we twist the filters and shift a little bit on the materials, we can have different appearances of the materials. And we find locations for these things, then it can become art from the crystal growth. So I was very much into that when I was more in the lab and so on. And I had a part of exhibitions 2 or 3 times in these things where it was exposed and so on. So the art and science is something which I have personal interest in. So with that, I hope I have given some Friday feeling of exciting things. Let's see if I can come to stop sharing. So now hopefully you can see me. And with this, I would like to thank you, Imran, for this opportunity and take any questions, discussions or ideas and so on.